In this video, we're going to continue our work with the direct uniqueness method. The conditional statements that we're going to be analyzing in this lesson are of the following form. If some statement C, then there exists a unique object X with property A. And what we want to do is develop a strategy to prove these kind of conditional statements. Now I want you to be able to compare and contrast to the last lesson. Notice that the three things from our last lesson are also present in these kind of statements. We have object X, we have property A, and we also have the word unique. What makes this statement a little bit different from our last one is we also have the phrase, there exists. This phrase implies that we're going to be using the construction method to show that there actually is an object X that has property A. The word unique here is going to imply that some of the methods that we're going to use to prove this conditional statement are going to be similar to what we saw in the last lesson. However, because of this new phrase, there exists, we're going to have to undergo a construction before we can do the uniqueness method. We have to show that at least one object X does indeed exist. In our last lesson, we didn't have to worry about construction because this phrase, there exists, didn't appear inside of our statement. The existence of object X was implicitly implied. So let's take a look at a strategy for these types of statements. The first thing we're going to do is deal with the there exists phrase. And to do that, we're going to actually try to construct an object X that has property A. After we're done with the construction step, we want to move into the uniqueness method. So moving into step 2, we're going to assume that we have two objects that both have property A. We're going to call those objects X and Y. And then just like we did in the last lesson, we're going to try to show that object X and object Y are actually identical. It's this step here where we show that X is actually the unique object with property A. In this example, we're going to have A be a 2 by 2 matrix. We're going to assume that the determinant of A is not equal to 0, and then our claim is that there exists a unique 2 by 2 matrix B satisfying A times B is equal to I2, where I2 is the 2 by 2 identity matrix. Since this is a smaller example, we can actually write out what A looks like. I'm going to call capital A the 2 by 2 matrix A, B, C, D, and I get the sense that this matrix B is going to actually be A inverse. So from linear algebra 1, we know the formula to calculate A inverse, so I'm going to say that B is probably going to be equal to 1 over determinant of A times the adjoint of A. So let's write in this information. The determinant of A is AD minus BC. By the way, we know that the determinant is not equal to 0, so putting this here in the denominator is totally okay. And the adjoint of A is formed by switching the values on the main diagonal. So A and D get switched, and then negating our other two entries, so negative B and negative C. So I have a feeling that this matrix B here is going to be this matrix that's going to satisfy the particular property that we're looking at up here. So trying to determine the form of B here is actually the construction part of our proof. And to finish off the construction portion of our proof, we have to show that this matrix B down here does satisfy A times B is equal to I2. So we're going to do that on the next slide. So multiplying out our two matrices A times B, we're going to get ABCD times the fraction 1 over AD minus BC times the adjoint of A, which is D, negative B, negative C at A. Now this fraction here is a scalar number, so I can move it out front of our two matrices. And that's going to give us 1 over AD minus BC. And then we're going to get a multiplication of two matrices here, A, B, C, D. And D minus B minus C, A. So just to keep things a little simpler for us, let's multiply these two matrices out first. And when we distribute this fraction into all of the values of our matrix, we are indeed going to get the 2 by 2 identity matrix, I2. So this tells us two important things. The first one is that this constructed matrix B satisfies the property A times B is equal to I2. And the second thing it tells us is there is at least one matrix that satisfies this particular property that we're looking at. So what we're going to do is we're going to assume there's another 2 by 2 matrix. We're going to call it capital C, and it also satisfies the particular property of interest. So A times C is equal to the 2 by 2 identity matrix. And our goal is to show that B is actually equal to C. So let's begin with B in this case. We know that B is equivalent to B times the 2 by 2 identity matrix. This is a property of the identity matrix. And now we know that I2 can be replaced with the expression A times C. So this is really B times A times C. And we can do a little bit of regrouping with our brackets here so that we do the multiplication B times A first. Now, while we didn't explicitly show it in our proof, it is true that the multiplication of our matrix capital B times A is equal to the 2 by 2 identity matrix. So you should take some time now to prove that on your own. We are going to assume that this is true, so that B times A times C is equal to the 2 by 2 identity matrix times the matrix C, and I2 times C is of course equal to C. And this gives us that equality that we need. Now we know that B is equal to C, so B must be the unique 2 by 2 matrix satisfying that property. In our next example, we're going to have A, B, and C be real numbers, and we're going to define a new operation. This operation is going to be called A circle B, and A circle B is going to be defined to be A plus B minus 1. What we'd like to do is prove that there exists a unique solution, we're going to call that solution X, to the equation A circle X is equal to C. Now notice that our phrase there exists does appear inside of the statement, so we have to go through the construction procedure first. We're actually going to construct a solution X and show that it satisfies the property A circle X is equal to C. So let's look at this equation A circle X is equal to C. And what we want to do is we want to replace the left-hand side with A plus X minus 1. So this is the definition of A circle X, A plus X minus 1, and this is going to be equal to C. And now we're going to solve for X. So I'm going to move the A and the negative 1 over to the right-hand side, and we're going to have X is equal to C minus A plus 1. So here's our candidate for the unique solution to the equation A circle X is equal to C. So now that we've constructed a possible solution to this equation, A circle X is equal to C, let's show that it does indeed satisfy the equation. Making the substitution, we get A circle C minus A plus 1, and using the definition of our circle operation, this is going to give us A plus C minus A plus 1 minus 1. And if we drop the brackets, we'll notice that the A's are going to cancel and give us 0, and the 1's are also going to cancel and give us 0, and we're going to be left with just the real number C. So this tells us that the solution that we've created does satisfy the property A circle X is equal to C, so we know there's at least one solution to this particular equation. Now we're going to work through the uniqueness method. We're going to assume that there are two solutions to this equation, and try to show that they're actually the same object. So let's call this second solution Y, and we know that Y is also going to satisfy the property A circle Y is equal to C. If this is true, we know that both A circle X and A circle Y are equal to C, so we can set them equal to each other. And then we can use the definition of the circle operation, so the left-hand side is going to expand out and become A plus X minus 1, and the right-hand side is going to become A plus Y minus 1. And notice that we can add 1 to both sides. That's going to give us A plus X is equal to A plus Y. And A is a real number, so we can subtract that from both sides of our equation, and we're going to get X is equal to Y. And this tells us that X is the only solution to this particular equation. Hey everyone, thanks so much for watching this video. If you click here, over here on this beautiful YouTube logo, you can head over to my channel to see some videos for my other math courses. You can also follow me on Twitter for updates for your course or to ask questions. Alright, my little epsilons, stay positive.